All right, so we have a balanced equation and we have a table. You're not always going to get a table or need a table, because hopefully by now you realize that if you read the problem you have to solve, you really only need a couple numbers derived from this balanced equation. So if we read this first problem, it says what mass of Al2O3? I'm going to need to know, based on my ideal mole ratio here, based on this 4:3:2 ratio, what is this, what's the equivalent in grams of Al2O3? And what's the volume of the oxygen that I need? Here's my oxygen. I go down to the volume row, liters of oxygen, because liters of oxygen is in the problem. Now it says excess of aluminum, so that means you're not going to run out of aluminum. You don't have to worry about aluminum. Just completely ignore anything that says excess. That's a good thing. You've got plenty of it. Don't worry about it. But what you do need to know is when you're thinking about making product, how high does your Al2O3 bar go? How high does it get? How much can you make when, if you start with 3.23 liters of oxygen and you use it all up, when this hits 0, when there's no more oxygen left, how high does this go? So that's the problem we're trying to solve here. So we're going to start with 3.23 liters of oxygen. You must have on your paper a number, a unit, moles, mass, or grams, or grams or liters, a number, a unit, and a chemical formula. Now, basic dimensional analysis here. If I want liters of oxygen to cancel, I put it here. If I want to end with grams of aluminum oxide, I put G of Al2O3 up here. So I set it up like this, then I go back and worry about the numbers, and things just kind of fall into place. So I got grams of aluminum oxide. So I look over here and I say, what number would be in this box? The best thing to do, although you can solve this a couple different ways, you can distribute if you want and figure out what they each are, but I recommend just figuring out what one of these weighs and then multiply it by the coefficient. So aluminum oxide, 2 aluminums plus 3 oxygens, when you add that up, it comes out to about 102 grams. Then multiply by 2 because there's 2 moles of them. So the total mass of 2 moles would be 204.0 grams. So that's how I know 204 goes here. Then liters of oxygen, I see the 3 out front and I say to myself, well, I know every 1 mole has a volume, assuming it's a gas, of 22.4 liters. I don't have 1 mole, I have 3 moles, so 3 times 22.4. Doesn't matter what kind of gas this is. It could be oxygen, hydrogen, neon, nitrogen, whatever, doesn't matter, as long as it's a gas and you pay attention to the coefficient. So 3 times 22.4 is 67.2 liters. That's my number here. And then I solve. Normal old dimensional analysis. 3.23 times 204 divided by 67.2. And I should get 9.81 grams of Al2O3. What does this mean? That's how much product, that's how high this bar will go. It'll go up to the 9.81 gram spot when all of my oxygen is used up and hits 0. I can't make any more. All right, now there's another problem using the same ratio, the same balanced equation. So let's solve this one. It says how many moles of oxygen must be present in order to allow 250 grams of aluminum to completely react. So if I've got my bars here, I've got 250 grams of aluminum, I want to know how high does my moles of oxygen bar have to be so that when this hits 0, that hits 0 also. How high does this have to be so that aluminum gets a chance to be used up before the oxygen used up? Because if oxygen hits 0 first, then there's going to be some of this left. But we want to completely react all 250 of this, and we need to know how much oxygen to go with it. So 250 grams of aluminum, a number, a unit, and a chemical formula. You want the chemical formula down here because you want it to cancel. So grams of aluminum goes here. And we want to end with moles of oxygen. Love moles. Nice and easy. Just take the coefficients. So you got to write moles of oxygen. Then you look up at your table and you say, if I had to fill out this whole table, what numbers would I put where? We'll switch over to blue here. So first we want moles of oxygen. This is easy. All I do is take the coefficient. 3 moles of oxygen. Again, it doesn't matter what kind it is. Just look at your coefficient. Grams of aluminum. So I look up here and I say, well, I've got 4 moles of aluminum to react with every 3 moles of oxygen, but I need to know what this is in grams, so I'm going to do a conversion here. I know that 1 mole of aluminum, look on the periodic table, 27.0 grams. But I have 4 moles, so 4 times this. So this is going to be 108 grams for all my aluminum that I need to go with my 3 moles of oxygen. So this is the ratio that I get from my balanced equation. In a perfect world, this is exactly what I would need to go together. I'm going to be using more than 108 grams, so I have to figure out what the equivalent is, and I use that same ratio. So 250 times 3 divided by 108, final answer is about 6.94 moles of oxygen. So I would need 6.94, this is a different unit here because we got moles. I need almost 7 moles of oxygen. And as long as I have about 7 moles of oxygen, I can use up all my aluminum. But if I have anything less than this, if I have anything less than about 7 moles of oxygen, that's going to run out first. And I'm still going to have extra aluminum. I can't use all 250. So that's what this problem is solving. All right, let's look at another problem where you don't have a table to rely on. So you can make one, I suppose, if you have to, or you could just use your imagination. So the question says, a fertilizer company has this much hydrogen gas, 550 liters of hydrogen gas in their stockroom. They want to make as much nitrogen trihydride, we know that's NH3, as possible. What volume of nitrogen gas do they need in order to react completely with the hydrogen gas and not have any reactants left over? So we know that they have 550 liters of this. What we need to know is how much of this do they need so this doesn't run out first. How much of this do they need, of the nitrogen do they need, so that when this runs out at the same time. Now we know it's a 3-to-1 molar ratio. We need 3 moles of this for every 1 mole of that. But this is talking in terms of liters, in terms of volume. So we have to switch this information over to volume. So I'm going to start with the number they give to me. So 550 liters of hydrogen. I want to cancel out hydrogen, so I'm going to put hydrogen down here, and I'm going to, liters of hydrogen, and I'm going to put liters of nitrogen up top because that's what I want to go to. So I just need to worry about what numbers would be here. Now, this is volume. It has to be for gases. I don't care what kind of gas it is as long as it's a gas, and I use the coefficient. So hydrogen, 3 moles times 22.4 each. Remember, 1 mole is 22.4 liters. 3 times that is 67.2 liters. This is 1 mole, so that's easy. That's just 22.4 liters. So nitrogen, 22.4, that would be in my table. Hydrogen, 67.2. So then you do the math. 550 times 22.4 divided by 67.2 is about 183.3 liters of nitrogen. About 183. So now I know if I have 550 liters of hydrogen, I would need 183 liters of nitrogen to go with it. So if I have these two amounts, then they'll both hit 0 at the same time. They'll both react and not have any reactants left over. If I have anything more than this, I'll have extra nitrogen. This will run out first. And if I have anything less than this, this will run out first, and I'll have excess of this, neither of which is a good situation. So I want about 183 liters of nitrogen left over, or to use rather.